You ever wonder how your music playlist just knows what song to play next? Or how that undo button in your text editor can rewind your every mistake? Well, a lot of the time, the secret sauce is a really simple but super powerful idea, the linked list. Today, we're going to pull back the curtain on the singly linked list, a true building block of the software we use every single day.
Okay, to really get a handle on a linked list, it helps to compare it to something you probably already know, the array. An array is kind of like a bus. It's got a fixed number of seats, all in a row, all part of one solid structure. Now, a linked list, that's more like a train. Each car is its own thing, and you can add a new car or remove one anywhere you want. All you have to do is unhook and rehook them. That's because the cars don't have to be physically next to each other in the computer's memory. They can be all over the place. So here's our game plan. We're going to build a linked list right from the ground up. We'll start with its smallest part, the node. Then we'll see how we chain these things together. After that, we'll actually use it, see what it's good at, what it's not so good at, and finally, we'll cover the common mistakes you absolutely want to avoid. All right, let's start with the absolute core concept. Everything, and I mean everything we're about to talk about, is built on this one simple piece. This is it, the node, and it's only got two jobs. First, it holds some data. You know, a number, a piece of text, whatever you need to store. The second part is what we call a pointer. Just think of it like an arrow or a signpost that points to the next node in the chain. It's the link in our linked list. That's it. And visually, this is all it is. A box with your stuff in it and an arrow pointing to the next box. This simple little package is what gives the whole structure its flexibility and power. So, we have our building blocks. Now, let's actually build something. Let's see how we snap these nodes together to make our train. Building the chain is pretty straightforward. First, you need a starting point. We call this the head. The head isn't a node itself. It's just a special pointer whose only job is to remember where the very first node is. Once you have that, you just create new nodes and update the next pointer of the previous node to point to the new one. So here's our start. We create the head pointer and our very first node. And just like that, the list exists. Now, look closely at that next pointer. It's pointing to something called null. That's basically a stop sign. It's a special value that just means, hey, there's nothing after me. It tells us we're at the end of the line. Now, let's add another node. It's easy. We make our new node, which holds the number 20. Then we go back to our first node, and we change its next pointer. Instead of pointing to the null stop sign, it now points to our new node. See? The chain is getting longer. And here's the final chain. Each node points to the next until the very last one hits that null stop sign. Now, this is absolutely crucial. That head pointer is our only way into this list. If we accidentally lose the head, the entire list is just lost in memory. The nodes are still there, but we have no way to find them. It's a big deal.
Okay, our list is built. Now what can we actually do with it? Let's walk through some of the most basic things you'd want to do.
So, the most common operation is just reading what's in the list. We call this traversing. It's just a fancy word for visiting each node one by one. To do this, we create a temporary pointer, let's call it current, and we start it off by pointing at the exact same place as our head. From here, it's a simple two-step dance. First, we read the data in the node that current is pointing to. Then we just tell current to move to the next node by following that next pointer. Easy as that. And we just repeat that process. Read the data, then follow the next pointer. We keep doing this over and over and over until our current pointer hits that null value. Once it's null, we know we've reached the end and we're done. So what about adding new stuff? Well, this is where linked lists really shine. Inserting a new node right at the beginning is crazy fast. You just create your new node, you tell its next pointer to point to the old head of the list, and then you update the main head pointer to point to your new node. Done. It's a super quick three-step shuffle.
So you might be thinking, okay, this pointer stuff is cool, but why not just use an array? That is a great question. And the answer, like with so many things in programming, is that it all comes down to trade-offs. This chart basically says it all. Let's go back to our bus and train. If you want to get to the 50th person on the bus, you just walk to seat number 50. It's immediate. Programmers call that O of 1 time. But on the train, to get to the 50th car, you have to walk through the first 49 cars. The time it takes depends on how long the train is. That's O of n time. But what if you want to add a new car to the very front of the train? Simple. You just hook it up. That's O of 1. Try doing that on the bus.
You'd have to make every single person get up and move back a seat. That's slow, O of N. That's the trade-off.
Now, linked lists are powerful, for sure, but they also come with a few classic traps that you really have to watch out for.
All right, there are a few big ones. First, memory leaks. When you're done with a list, you have to go through and delete every single node to free up that memory. If you don't, those nodes become ghosts, taking up space, but impossible to get to. Another big one is trying to read data from a null pointer. That'll crash your program, guaranteed. And of course, the worst mistake of all, losing track of your head pointer. If you do that, the whole list is just gone. And this quote right here, it nails a huge risk. If you're not careful, it's so easy to lose track of nodes, and they'll just sit there, silently eating up your computer's memory. Over time, that can slow your whole application down, or even cause it to fail completely. So that brings us to one last thought to chew on. We've seen that in a singly linked list, we can only go forward, right? Following those next pointers is like driving down a one-way street. But what if you needed to go backwards? What if you needed to reverse? What kind of data structure would you reach for then? Something to think about.